Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at flow meters. In the previous set of videos, we looked at electromagnetic flow meters, ultrasonic flow meters, Doppler flow meters and time transit flow meters. In this video, we will look at two specific types of flow meters, pulsed flow Doppler and laser Doppler flow meter. Before we proceed, let us discuss some of the limitations of the continuous wave Doppler flow meters. First of all, the assumption of this method is that velocity profiles are smooth or uniform. They are usually not blunt or not uniform or smooth. Right. Why is that? Because different cells move at different velocities. Why would different cells move at different velocities? Because their masses might be different, their sizes might be different, because of various reasons. Different cells move at different velocities. This essentially causes a change in the frequency shift that happens with Doppler. Changed shift. This is one, because we are only measuring the shift in the frequency. One of the reasons why the shift might happen is because of this, but this is not actually seen, because what you are measuring is the shift, the net shift that is happening due to the velocity itself, but some of it may also be due to differential velocities of different cells. Another reason is that a single cell is at the beam intersection junction, the measurement site, only for a very brief amount of time. This essentially leads to a situation in which what you are measuring at the output is a time gated function of frequencies. Time gated frequency function. Now, this again leads to changed shift in the frequencies. Another reason that we have previously seen is that at different angles to the beams, the velocities measured are different. So, you need an angle factor. That is another thing. The other thing could be that cells whose velocities are being measured might be tumbling, or they might move due to turbulence, right? And the velocities might change not because of the physiological phenomenon, but maybe due to tumbling, turbulence and other physical phenomena. These are all the things that are some of the limitations of the Doppler method in general, continuous wave Doppler in particular. So, we are interested in getting a more accurate picture. For that, we go for what is called as the pulsed flow Doppler. Why is this needed? Because the continuous wave Doppler flow meters essentially lack flow profile detail. You get a single number, you do not get a profile, that is within the blood vessel, what is the velocity profile that you are having, this or is it this, what is the profile of velocity that you are having, or is it this, for example. There is a difference between these physically. This is because the continuous wave measures flow at a particular point, at a particular point in space, at a particular point in time. But you need to measure velocities at that depth, at that depth, at that depth, at that depth and that depth to reconstruct this velocity profile. That is being done by the pulsed Doppler. Pulsed Doppler essentially provides the velocity values at various depths by using time delayed echoes. What is the working principle? What is the method? Essentially, this function similar to a radar, right. So, this one similar to a radar. How is a radar working? Since a brief pulse of, in this case, sound wave, a brief pulse of a sound wave, this brief burst ultrasound is transmitted. The transmitter itself can serve as a receiver, because there is a time delay between the transmission and the reception. Why is there a time delay? Because there is a constant or a non-zero amount of time that it takes to reach the particular point of interest. Where it is coming from, how much delay is there, is an indication of where you are going, where the target is. So, the depth is indicated by the time delay itself, and you examine at various depths, you examine the frequency shifts at a given depth. Using the frequency shift, you reconstruct the velocity. At a different depth, you reconstruct the velocity. How do you know the depth? By the delay. So, for various delays, you reconstruct the velocities using the frequency shift, essentially creating a velocity profile, a flow profile across the blood vessel. There are some constraints or trade-offs that are involved in this. Right. What are the trade-offs? Well, there are essentially two trade-offs. One is range resolution, the other is signal to noise ratio. Short pulses provide high range resolution and long pulses provide better signal to noise ratio and ability to discriminate small velocities. It turns out that there is a sweet spot between the two, and that sweet spot has been known to be the 8 megahertz signal, for a duration of 1 microsecond. Well, 1 microsecond duration. Okay, we will discuss that in a little bit. Now, this essentially leads to a situation in which I can have both better range resolution and better signal to noise ratio. To avoid confusion about the range or the ambiguities of range, there are essentially these two constraints. One is range ambiguity, the other is the sampling theorem, Nyquist criterion, right. To avoid range ambiguities, the frequency FR must be less than C divided by 2 times Rm, where Rm is the maximal useful range, and if you use sampling theorem, Fr is greater than 2 times Fd. Now, I combine these two equations or inequalities. In this case, what is Fr? Fr is the pulse repetition rate, Now, if I combine these two, I essentially get an inequality that has a product of maximum velocity and the maximum range times cos theta, where theta problem is always there. So, essentially I have a product of the range and the maximal velocity is a function of c squared by 8 times Fo, where Fo is the source frequency. Now, that means because these two are products um times R max or u max times R max, I cannot maximize both simultaneously. I can have an optimum between the two, but I cannot have maximum in the two because these two are products. Are there any more constraints? Other than these? The answer is yes, there are other constraints. The measurements are even more constrained. Why is that? One is because because your pulses are of a very brief duration, that is they are time limited signals, there is going to be spectral leakage, a sort of a spectral spreading that is going to happen. That is, there are going to be the original frequency and its sidebands that are going to come into the picture, right. There are going to be higher frequencies than originally indicated. Spectral spreading due to short or brief pulses that are sent. This is the other constraint. These are the constraints. What else? Anything else that we can think of? The other is relatively poor anti-aliasing characteristics, filter characteristics. That is, you cannot have a sudden cutoff frequency in the low pass filters that you use. You cannot have filter characteristics that approach, for example, that approach the ideal filter characteristics. That is not practical filter characteristics will not be ideal, and that means that there will be a slope, there will be time taken, or there are other problems. If you increase the order of the filter, the other problems regarding stability and other things come into the picture. So, it is not really that. Poor anti-aliasing filter characteristics are LPF, low pass filter characteristics, leading to aliasing. That is the other problem that could happen. The other thing we discussed previously is that 1 microsecond duration, we discussed this previously, is that the electrical circuit can be switched on or off at 1 microsecond, but the sound, the acoustic circuit or the acoustic crystal cannot turn itself off immediately when you turn off within that 1 microsecond. So, there will be ringing that happens in the crystal or at its resonant frequency. This leads to a situation in which, although the electrical circuit is turned off, the sound is getting generated. This is because the Q factor for these oscillators are relatively high. You could reduce the Q factor by artificially adding a mass to the oscillating crystal, but then if you reduce it too much, then what happens is that there is a general inefficiency that is built into the system, which is not a favorable situation. Whereas, if I change the Q factor or keep the Q factor at a very high value, then what happens is ringing will always be there. So, essentially you need to keep the Q factor at an acceptable value where some ringing is there and some efficiency is also there. So, you are able to keep both ringing and the efficiency. We will end this class with this. We will continue the laser Doppler in the next video. So, with this we come to the end of this video. In this video, we looked at the pulsed Doppler flow meter measurement and the constraints that it is working with. Okay. Thank you very much for your attention.